Hi everyone. Today we are going to discuss about examples of boundary linear operators. In the last class we have discussed about how to define a boundary linear operator and how to define a norm for a boundary linear operator. And today we are going to see many examples and how to compute the norm of an operator. So the title for today is examples of boundary linear operators. Let me quickly recall that if T is a linear map, then T is bounded if T of any bounded set B is bounded in H2 whenever B is bounded in H1. So this is the definition, and we have shown equivalent conditions. So the following are equivalent. The first one is T is bounded there exists some constant K such that norm Tx in the inverse space H2 is then K times norm X for every X in H1. And the third condition is T is continuous on H1, and that is equivalent to saying that T is continuous at 0. We can take any arbitrary X, also say that T is continuous at X instead of fourth condition. And the fifth one is T is ellipsis continuous. That means there exists some constant K such that norm of Tx minus Ty less than or equal to K times norm X minus Y for every Xy in H1. These are the five equivalent conditions we have seen for a operator to be bounded. So let us, if we start here, we have to start a linear transformation. So then the following are equivalent. This is one of the important results. And we have seen that when T is bounded, this quantity we defined as supreme of norm Tx by norm X. X is in H1, X in H0. This quantity is finite, and we have called this as the norm of the operator or operator norm of T. And we have shown that there are equivalent formulas for the same definition of norm. So that is nothing but supreme of norm Tx, where X is in H1, norm X less than or equal to 1. This is the second one, and this is the third one, norm Tx, where X is coming from H1 and norm X is 1. And the last one is infimum of all those positive numbers K such that norm Tx is less than K times norm X for every x in h1. So we have shown these all different formulas gives the same quantity called the norm of the operator. Most of the time we will be using the third condition, and we have explained in the last class that the fourth condition give a geometric interpretation. This gives the geometric interpretation, and in fact it also suggests us how to find the norm of an operator. So here let me quickly how to find the norm of an operator. So the first step is, so to find norm of t, so first step is find a number k such that norm tx less than or equal to k times norm x for all x in h1. This only guarantees that t is bounded. So this implies that t is bounded, and we have to find the optimal k satisfying this inequality, and then only we can find the norm. So the second step is, if there exists some x in h1 with norm x equal to 1 such that norm tx, let me say this is x naught, norm t, then we can say that k is exactly norm of the operator. So these are the two steps to find the norm of an operator, and sometimes it may be possible that the second condition may fail. In that case, what exactly we are going to do is that we find a sequence of unit vectors xn such that norm txn goes to norm t. Then we can conclude that norm of t is exactly the constant that k that we have chosen in the first step. So these are the two important steps to find the norm of an operator. So also recall that we have also studied two examples. The first one is when t equal to lambda times identity on the Hilbert space H, and lambda is a complex number. We have shown that norm of t is exactly mod lambda. And the second one, so when t is a map from C2 to C2, lambda 1, 0, 0, lambda 2, this is diagonal matrix. So this is a map from C2 to C2. Then we have shown that norm of t is exactly maximum mod lambda 1 comma mod lambda 2. So these are the two examples we have studied in the earlier class. Today we are going to study more examples of boundary linear operators and how to find the norm of such operators. So let us look at a third example. Let us take h1 be a finite dimensional Hilbert space with an orthonormal basis. Let us call phi 1, phi 2, phi n. So dimension of h1 is n, and h2 arbitrary Hilbert space. H2 be and another Hilbert space. Of course, both are complex Hilbert spaces. So let us take a linear map. Let t from h1 into h2 be linear. What we want to show that the claim is that t is bounded. T is So as I told earlier, finding or saying that T is bounded, it is enough to find a K positive such that norm Tx less than or equal to K times norm x. From that we can conclude that T is bounded. But finding the norm, we have to work a little bit more. So let us look at this part. So since if you take x is in H1, from this we can conclude that x can be expressed using this orthonormal basis of H1. So this is inner product x phi j multiplied by phi j. So T is linear. We can say that Tx is summation j equal to 1 to n inner product x phi j multiplied by here T phi j. Now let us try to look at, so consider norm Tx square. So this is the, we can look at norm Tx. So this is norm of summation j equal to 1 to n inner product x phi j T phi j. Now we can apply the triangle inequality, summation j equal to 1 to n. This is modulus inner product x with phi j norm T phi j. So here if we apply the Cauchy square inequality for modulus of inner product x with phi j, since norm phi j is 1, so this is less than or equal to summation j equal to 1 to n norm T phi j we will get, and this part is you can take as k. So from this we can say that T is bounded. So this is one way of looking at the this is one way to say that T is bounded, but let us consider, let us take in a different way. So norm Tx is less than or equal to summation j equal to 1 to n mod x inner product of modulus of inner product x with phi j multiplied by norm T phi j. So here if you apply the Holder's inequality, we can get a better bound than whatever we got in the earlier step. So by the Holder's inequality, we can say that summation j equal to 1 to n modulus of inner product x with phi j square root of this multiplied by summation j equal to 1 to n. So by Holder's inequality. So let me quickly recall the Holder's inequality. So if we take a1, a2, so on an, and b1, b2, so on bn, which are complex numbers, then we can say that summation j equal to 1 to n mod aj mod bj, this is less than or equal to summation j equal to 1 to n mod aj square root of this multiplied by summation j equal to 1 to n mod bj square power r. So Holder's inequality for p equal to 2. For general p and q, if you take which are positive numbers such that 1 by p plus 1 by q equal to 1, then also we can replace in the first for the first factor we can replace power p whole power 1 by p, and here also power q whole power 1 by q, but we are taking only p equal to q equal to 2. So by that inequality, actually what we can do is we can get a different bound. So from this we can conclude that norm of Tx less than or equal to, so k times where your k is summation j equal to 1 to n norm t phi j square whole power 1 by 2. So we get a different k. Okay, so from this we can conclude that the operator that we have defined, that domain is when the domain is a finite dimensional Hilbert space. So even the map is linear, you are able to show that it is bounded. So the conclusion is the following. That if H1 is finite dimensional, then we can conclude that L of H1, H2 is exactly the space of all bounded linear map. So we know that L of H1 is a vector space. So from this we can conclude that B of H1, H2 is a vector space. Not only that, we can also show that B of H2, H1, H2 is a vector space, irrespective of whether the spaces H1 and H2 are finite dimensional or not. Okay, so this gives one important example of a linear map which is automatically bounded. Now we can ask the following question. If H2 is finite dimensional and H1 is an arbitrary Hilbert space, can it happen that L of H1, H2 is exactly B of H1, H2? In other words, can we say that a linear map defined from H1 into H2, where H2 is finite dimensional Hilbert space, is bounded or not? Okay, in general this is not true. We can actually, the hint is that define a functional so which is linear but not bounded. We can always get such functions. Okay, so from that we can conclude that even though H2 is finite dimensional, a linear map need not be bounded. Okay, let us look at a few more examples. Let us take a complex matrix M cross N, complex matrix. That means AIJs are coming from complex numbers. So let us take, so define T from Cn to Cm by T of x1, x2, so on xn as this A of x1, x2, so on xn. So by the earlier example, we can conclude that T is bounded because we can easily show that because of A is a matrix, so this is linear. So clearly T is linear and bounded by earlier example. Now important thing to show is that norm of t less than or equal to summation ij equal to 1 to n mod aj square so norm of t is bounded by this fixed quantity which depends on the entries of the matrix. Now it is very interesting to find when this inequality become equality. The question is the following. When is the inequality become equality? When can this happen? We can actually find out a few cases where this equality happens, but in general this is not true. In the case of 2 by 2 matrices, we can write this explicitly, which is a very complicated expression, but it is possible to find norm of t explicitly when m equal to 2 and n equal to 2. Okay. So let us look at a few more examples. Which generalizes the earlier examples. So let us take a bounded sequence of complex numbers. This is in L infinity. Define t from L2 to L2 by t of x1, x2, x3, so on equal to lambda 1 x1, lambda 2 x2, lambda 3 x3, so on. So for every xn coming from L2. Here L2 means L2 of natural numbers. Now we want to show that this is linear and bounded. The claim is the following. T is a bounded map on L2, and not only that, norm of T is exactly supreme of mod lambda n, where n is in n. In other words, this is subnorm of the sequence lambda n. This is what we want to prove. So checking that T is linear is trivial. So check that T is linear. Now we want to find whether this is bounded or not. Okay, so let us look at for simplicity, let us write x as this sequence x1, x2, so on xn. Then we can say that norm of tx, so that is nothing but summation j equal to 1 to n mod lambda j lj square over power 1 by 2. Now this this is j equal to 1 to infinity. Now this is less than or equal to m times summation j equal to 1 to infinity mod lj square. So m square, so where we can take m to be supreme of mod lambda n is coming from n, because if mod lambda j less than or equal to m, then we can actually norm tx less than or equal to m square. So this is nothing but norm of tx is less than or equal to, so here 1 by 2 will come, here also 1 by 2. So on the whole, this is nothing but m into L2 norm of x. So this is nothing but, so from this we can say that T is bounded and we can say that norm of T less than or equal to m. Now the question is that can this inequality become equality? So let us look at that part. So let En 0, 0, 0, 1 in the nth place and remaining all positions are 0. Okay. Now if you look at T of En, it is exactly lambda n En for every n. Okay. Now let us start with some epsilon positive. Okay. Now m is supreme of mod lambda n. So for this epsilon, there exists some n naught in n such that you get mod lambda n naught is bigger than m minus epsilon by definition of the supremum. So that means if you look at T of, this implies T of En naught is lambda n naught En naught. So this implies, so we can actually, so we have norm of T is bigger than or equal to norm of T En naught L2 norm. So but this is mod lambda n naught and norm of En naught. So that is 1, and we know that mod lambda n naught is bigger than m minus epsilon. Now this happens for every epsilon. So this from this we can conclude that norm of T is bigger than or equal to m. So hence we can conclude that norm of T is exactly m. Okay, so if you observe this example, we have not found a unit vector, let us say x, such that norm Tx equal to m. So that is not possible here, but we were able to approximate it, the norm of the operator in this way. So next we discuss about matrix of an operator. So the idea for discussing or the motivation for discussing this concept is that earlier operator, whatever we have defined on L2, that gives an infinite matrix, which is a generalization of finite dimensional setup. So let us start with a separable Hilbert space. Let H be a separable Hilbert space. With an orthonormal basis. Let us take, this is B, P1, P2, P3, so on. And let us take T to be a bounded linear map on H. Then the matrix of T with respect to B, the orthonormal basis, is given by so this is, let us say it is Aij, where actually we can define Aij is inner product of T Ej inner product with I. So this is similar to the matrix of a linear transformation defined on the finite dimensional space. This is exactly a generalization. Okay. Now with respect to the standard orthonormal basis of earlier operator, so let us quickly recall that we have defined T from L2 to L2, T of x1, x2, x3 going to lambda 1 x1, lambda 2 x2, lambda 3x3, so on for every sequence in L2. Now let us take B to be the standard orthonormal basis that we have already defined earlier. Then the matrix of T with respect to this is nothing but, if I look at the Aij element, so Aij is inner product Tej with Ei. But we know that Tej is nothing but lambda j Ej that we have already observed, and this is Ei. So this will be lambda j when I equal to j, and 0 when I not equal to j. That means the matrix of T, so this is A is nothing but only the diagonal entries are lambda j's and remaining are 0. So this is nothing but lambda 1, lambda 2, lambda 3, so on. So remaining are 0. So this is a diagonal matrix with the diagonal entries as lambda 1, lambda 2, lambda 3, so on. So this is an infinite by infinite matrix. So that means we can actually treat bounded linear operators on L2 as infinite by infinite matrices, depending, and this matrix changes with respect to the orthonormal basis, similar to the finite dimensional case. Okay. So this example, whatever we have discussed, generalizes the finite dimensional case. Okay, so next we discuss about one more example, which is again a generalization of the earlier operator we have discussed. So that is known as the multiplication operator induced by a function. So let us take A and B are real numbers with A less than B. Let us take a continuous function phi, which is a continuous function defined on the closed interval AB, which is either complex valued or real valued, does not matter. Define an operator which depends on phi, which we call as m suffix phi, from L2 of AB into L2 of AB by m phi at f. So m phi at f should be a function in L2. So acting on t, a variable in the closed interval AB, this is phi of t multiplied by f of t for every f in L2 AB and for every t in AB. So this operator is well known as the multiplication operator induced by phi. So induced by phi. Okay, so if you look at the earlier example, the infinite by infinite matrix, which gives the infinite by infinite matrix, whose entries are diagonal entries are lambda 1, lambda 2, lambda 3, so on. Actually, we have shown that norm of the corresponding operator is exactly supreme of mod lambda n, where n is in natural numbers. That means the sequence that we are taking determines the norm of the operator. Not only norm of the operator, we can actually say that it determines all the properties of the operator. So in this case also, we can say that the properties of m suffix phi are determined by phi. So that's why we call this as multiplication operator induced by phi. And in fact, if you know properties of phi, we can actually find out properties of M phi, and we will be looking at those properties at a later stage. Okay, our aim is to show that this is a bounded operator, and next thing to find is that norm of M phi. So let us consider. So to find norm, we want to consider norm of M phi acting on F. This is in L2. It's a L2 function. So this is norm of 2. So this is nothing but integral A to B. M phi f is multiplication. So mod phi of t f of t square dt whole power 1 by 2 by definition of the norm. And now we can say that this is less than or equal to sup norm of phi, because mod phi of t less than or equal to sup norm of phi, and this is integral a to b mod f of t square whole power 1 by 2. So this we can say that sup norm of phi multiplied by L2 norm of f. So this implies that norm M phi is less than or equal to sup norm of phi. Okay. From this we can only say that M phi is bounded. And it is easy to check that it's a linear map. So that is we can say that M phi is a bounded linear map on L to AB. Now we want to say that in fact we can show that this inequality becomes equality norm M phi equal to norm phi sup norm of phi. So that is a claim. Okay. Now since phi is continuous, it attains its maximum and minimum on the closed interval. So as phi is continuous, there exists some t naught in the closed interval AB such that mod phi of t naught is exactly sup norm of phi. This is possible. Now here we deal with two cases. The first one, case 1. So we assume that t naught comes from the interior of the interval. So then in this case we define a sequence of functions phi and t as follows, that you define root n by 2 when t is in this interval t naught minus 1 by n, t naught plus 1 by n, and 0 else. Now we can easily check that norm of phi n, so L2 norm of phi n is exactly 1 for every n. Now again we know that norm of the operator is always bigger than or equal to norm of the operator evaluated at a point. So we can say that norm of M phi evaluated at phi n. So this actually we can say that this is integral phi n is supported on the interval t naught minus 1 by n, t naught plus 1 by n. This is phi of t and root n by 2. So this is n by 2 come out mod square dt whole power 1 by 2. If you compute this one, so maybe I will rewrite it n by 2 into t naught minus 1 by n, t naught plus 1 by n mod pi t square dt. Okay, now we want to find out this value. So particularly we want to see what is the value of this one. Now we know that this phi is a mod phi t is continuous positive function. So by a known theorem, from calculus, we can find, so there exists Tn in this interval T0 minus 1 by n, T0 plus 1 by n, such that mod of phi of Tn square. So here we are going to use the following result. So recall. So if f is a continuous function defined on AB, implies there exists a point interior to the closed interval AB such that f of c is 1 by b minus a integral a to b f of t dt. So this is called the average of the function. So the average is attained at a point, interior point of the interval. Now you take a as t0 minus 1 by n, b as t0 plus 1 by n. So when you apply for this, when n varies, corresponding element also varies. So there exists a tn in this interval such that here f of t is nothing but mod phi t square. So mod phi tn square is nothing but, when you apply this result, this is nothing but 1 by length of the interval. Here length of the interval is 2 by n. So this is 1 by 2 by n multiplied by integral t0 minus 1 by n, t0 plus 1 by n mod phi of t square dt. So this is nothing but you will get n by 2 integral t0 minus 1 by n, t0 plus 1 by n mod phi of t square dt. So actually here look at this one, this quantity and this quantity we have defined here, both are same. So this quantity, both are same, so we can say that, so therefore norm of m phi is bigger than or equal to, let me call this as 1, this as 2. By 1 and 2 we will get this is mod phi of tn square. Now tn's are coming from the interval t0 minus 1 by n, t0 plus 1 by n. As n going to infinity, tn converges to t0, and since phi is continuous, so we can say that, so this is norm m phi is bigger than or equal to limit n tends to infinity mod phi tn square, that is nothing but mod phi of t0 square, that is nothing but is subnorm of phi square. Okay, so here we can actually take square, we can take square, this is the thing, and here yeah, so we can actually take this is square, so this concludes that norm of m phi is bigger than norm phi, and by the Euler inequality, which is an opposite, so from these two we can conclude that norm m phi, therefore norm m phi and norm of phi are same. Okay, now this example again can be generalized. Let us take x sigma mu be a measure space. We can take sigma finite measure space, which means X can be written as countable union of sets Xn whose measure is finite. So X can be written as union Xn and equal to 1 to infinity. This Xn Xm disjoint for all m not equal to n. Yeah, this one is not required. So we can say that mu of Xn is finite for every n. Such a space we call as sigma finite measure space. Now let us take phi from L infinity of S x sigma mu, which is the space of all essentially bounded measurable functions. So define m phi from L2 of x sigma mu into L2 of x sigma mu by m phi at phi is phi multiplied by f for every f in L2 of x sigma mu. So here phi f is a function in L2, so it is nothing but phi of t into f of t for every t in x. Now here also we can show that, so this is following the same steps as earlier. Check that m phi is bounded and m phi norm is exactly essential supremum of phi. This is essential supremum of mod phi. So essential supremum of phi is given by, you look at infimum of all those positive numbers k such that mod phi of t is less than or equal to k almost everywhere with respect to mu. So we can it's a mod phi is bounded almost everywhere, and take infimum of all such numbers. Okay, so when you take x to be set n and sigma to be the power set of all natural numbers, in this case n, and the mu is the counting measure, we get L2 of x sigma mu is nothing but L2 of natural numbers that we have discussed earlier. So in this case, we know that L2 of x sigma mu, capital L2 of x sigma mu is equivalence class of functions, whereas L2 of n in this case, it's exactly sequences. They are function from natural numbers n into C. So here each equivalence class contains only single element, hence this is usual sequences of functions. And phi, whatever we have taken, phi is replaced by the sequence lambda n. That means this generalized example, whatever we discussed now, is a generalization of the earlier example that we have discussed on a small L2. That means we have taken lambda n is to be in L infinity, and we have defined a multiplication operator, a diagonal operator with the diagonal entries lambda 1, lambda 2, so on. So that is exactly we can treat as a multiplication operator. So that is a particular case of this multiplication operator that we have discussed now. Thank you.